Welcome back, everybody. Ready for another deep dive?
Absolutely. Always ready to explore something new.
Well, today we're going deep into the world of machining tools.
Machining tools, huh? Sounds pretty specific.
It is, but trust me, it's way more fascinating than you might think. We've got some excerpts from a technical document all about these tools, and let me tell you, there's a lot more to it than meets the eye.
Oh, I believe it. I mean, I know a little bit about manufacturing, and even I'm curious to see what we uncover.
So first things first, why are machining tools such a big deal?
Well, think about it. Almost every object we use in daily life at some point was shaped or formed using a machining process.
From our phones to cars, everything.
Pretty much. And those processes rely heavily on these incredibly precise and durable tools. It's amazing how much engineering goes into something so small.
I'm already intrigued. So let's start with the basics. What are some of the key things to consider when choosing a machining tool?
One of the most crucial factors is the material of the tool itself.
Material, huh? Makes sense. I mean, you wouldn't use a plastic knife to cut a steak, right?
Exactly. In machining, different materials have different properties that make them suitable for specific tasks. The document we have here dives deep into four main types: ceramics, carbides, cermets, and industrial diamonds.
Okay, break it down for me. What's so special about each of those?
Well, ceramics are like the high-speed athletes of the machining world. They're known for their incredible heat resistance, which allows them to handle those high-speed, high-temperature cutting operations.
So they can really take the heat.
Oh, absolutely. But they do have a bit of an Achilles heel. They can be a little fragile when it comes to impact.
Ah, so not for those heavy-duty jobs then.
Yep.
What about carbides?
Carbides, particularly those made from tungsten carbide, are the workhorses of the industry. They're incredibly hard and wear-resistant, making them perfect for those tough, long-lasting cutting tasks.
Sounds like they're built to last. But I'm curious about those cermet materials. What are those all about?
The cermets are kind of like the hybrid athletes of the machining world. They combine the heat resistance of ceramics with the toughness of carbides, making them a great choice for applications where you need that balance of properties.
So the best of both worlds. Kinda.
You got it. Now, if you're dealing with incredibly hard materials, you might need to bring in the big guns, industrial diamonds.
Diamonds. Like actual diamonds.
You bet. Industrial diamonds are the ultimate cutting tool when it comes to hardness. But like any superstar, they have their quirks, they can be a bit brittle, and of course, they're a lot more expensive than other options.
Right. Diamonds aren't exactly known for being budget-friendly. This document also mentioned powder metallurgy, high-speed steel. What's so special about that?
It's a fascinating process, really. They take traditional high-speed steel, which has been used for decades, and enhance it using powder metallurgy techniques. This creates a more uniform structure within the steel, making it even stronger and more resistant to wear and tear.
So it's like high-speed steel 2.0.
Exactly. Stronger, tougher, and ready to tackle those demanding machining tasks.
Now, one thing that really stood out to me in this document was the ISO code for cutting tools. It looked incredibly complex. Is it some kind of secret language that only engineers understand?
It's not really a secret code, but it is a specialized language that packs a ton of information into a short string of letters and numbers. It's like a decoder ring that reveals everything you need to know about a cutting tool.
Okay, so what kind of information does this ISO code actually tell us?
It reveals the shape of the insert, the size, the tolerance class, how precisely the tool is made, you name it. It's like having a detailed blueprint right there in the code.
Wow. So a machinist can look at this code and instantly know exactly what type of tool they're dealing with.
You got it. It's a universal language that ensures everyone's on the same page.
That makes a lot of sense, especially when you're dealing with such precise tools and processes. I'm also curious about this thing called a chip breaker, which the document mentioned. It sounds almost like a safety feature.
You know, in a way it is. As a cutting tool shears through metal, it generates chips that can get very hot and, if not managed properly, can actually be dangerous. The chip breaker, this small groove or step on the tool, helps to break these chips into smaller, more manageable pieces.
So it's all about keeping those chips under control.
Exactly. It prevents them from building up and interfering with the cutting process, which can lead to all sorts of problems.
That's fascinating. It's like a tiny but mighty feature that plays a huge role in the overall machining process.
Absolutely. Even the smallest details can have a significant impact.
Speaking of small details, this document also delves into something called a rake angle. I'm picturing the angle of the cutting edge itself. Am I on the right track?
You are. The rake angle is crucial because it directly affects how the tool interacts with the workpiece. There are three main types: negative, neutral, and positive, each with its pros and cons.
Okay, lay it on me. What's the difference between these rake angles?
Well, a negative rake angle creates a stronger cutting edge, making it more durable. But the trade-off is that it requires more force to push through the material, which can generate more heat and pressure.
So it's a bit like trying to force a blunt knife through something tough, right? More effort required.
Precisely. Now, a neutral rake angle, as the name suggests, is all about finding a balance. It offers efficient chip removal and reduces pressure on the workpiece. It's like finding that sweet spot where everything just flows smoothly.
Okay, so neutral is like the Goldilocks of rake angles, not too extreme, just right. What about positive rake angles?
Positive rake angles are great for achieving a smooth and clean cut, but the cutting edge itself might not be as strong as with a negative rake angle. It's a trade-off between cutting performance and tool durability.
It seems like choosing the right rake angle is a bit like a balancing act, depending on the specific material you're working with and the desired outcome.
Exactly. Now, get this. Imagine taking those carbide tools we talked about and coating them with an incredibly thin layer of, say, titanium nitride.
Titanium nitride. That sounds incredibly high-tech. What's the benefit of doing that?
These coatings, sometimes only a few microns thick, can significantly improve a tool's performance. They reduce friction, increase hardness, and drastically enhance wear resistance.
So they basically give the tool a protective shield.
Exactly.
Yeah.
And there are various types of coatings, each designed for specific applications and materials.
It's amazing how much science and engineering go into something so tiny.
It really is. We've covered a lot of ground, but we're just getting started.
I'm ready for more. Let's dive into the world of external turning tools next.
Okay, external turning tools. So we're talking about the tools that shape the outside of a workpiece, right?
Yeah, exactly.
Right.
Like imagine you're working on a lathe, you've got this piece of metal spinning, and the external turning tool is what gives it that smooth cylindrical shape.
So it's basically like a sculptor's chisel, but for metal.
That's a good way to think about it. And just like with other machining tools, there are so many factors to consider when choosing the right external turning tool.
Like what? Give me some examples.
Well, you've got to think about the material you're working with, the size and shape of the cut you need to make, the desired surface finish, and even the clamping system that holds the tool in place.
The clamping system. I wouldn't have thought that would be
Well,
so important.
it's crucial. The clamping system needs to be super rigid to prevent any vibration or movement during the cutting process, any wobble or chatter, and you can kiss that precision goodbye.
Okay, so a solid clamp is key. What about the ISO code for external turning tools? The document mentioned that it gets even more specific.
You're right. For external turning tools, the ISO code includes additional information that's relevant to those types of operations. For instance, you'll see things like the tool's nose radius.
Nose radius, what's that?
It's the radius of that little rounded tip on the insert. It affects the shape of the cut and the surface finish you'll achieve.
So a larger nose radius would create a smoother finish.
Generally, yes. But it also depends on other factors like the feed rate and the material you're cutting. It's a bit like choosing the right paintbrush. For a painting, different brushes create different effects.
I'm starting to see how much thought and precision go into every aspect of machining. What about internal turning tools? Those must be even more specialized, right?
They are. Internal turning tools are used to machine the insides of things, like holes and bores, and they face their own unique challenges.
Like what?
Well, one of the biggest challenges is dealing with that overhang. When the tool has to extend a long way into the workpiece to reach the cutting area.
I'm guessing that creates a lot of vibration.
Exactly. The longer the overhang, the more prone the tool is to vibrating, which can wreak havoc on your accuracy and even damage the tool itself.
So it's a bit like trying to write neatly with a very long pencil. The further out it extends, the harder it is to control.
That's a great analogy. That's why engineers have developed all sorts of clever ways to combat vibration, like using special anti-vibration bars and carefully selecting the right cutting parameters.
So a delicate balancing act between reach and stability.
You got it. And that balance becomes even more crucial when you're dealing with deep holes.
What about the ISO code for internal turning tools? Does that differ from the code for external turning tools?
It's similar, but it includes additional information that's specific to internal turning. For instance, you'll find details about the minimum hole diameter the tool can handle and the maximum cutting depth.
So again, it's all about providing that precise, detailed information that machinists need to choose the right tool for the job.
Absolutely. And just like with external turning, the clamping system is super important for internal turning tools. It needs to be super rigid to minimize any chance of vibration.
Solid as a rock. What about the rake angle for internal turning tools? Does that play a role as well?
Of course. For internal turning, a positive rake angle is often preferred because it reduces cutting pressure, which is especially important when you're working inside a confined space.
I can see how too much pressure in there could be a problem. It's like trying to squeeze through a narrow doorway with a heavy backpack.
Exactly. You don't want the tool to bind or break. And speaking of reducing friction and wear, guess what plays a big role here?
Those amazing coatings we talked about earlier.
You got it. Coatings like titanium nitride and titanium carbonitride can significantly improve the performance and longevity of internal turning tools, just like they do for external turning tools.
Seems like coatings are a game changer for all sorts of machining tools.
They really are. And now let's move on to another important aspect of machining: grooving and parting operations.
Grooving and parting. I'm picturing those tools that are used to create grooves and separate parts.
You're right on track. These operations are essential for creating all sorts of features on workpieces, from simple grooves to complex slots and even separating parts completely.
So it's like the cutting tools are performing surgery on the metal.
In a way, yes. It requires a high level of precision and control to achieve those clean, accurate cuts. And just like with other machining operations, choosing the right tool for grooving and parting is crucial.
I'm guessing things like the width and length of the cutting blade are important.
Absolutely. You need to match the blade width to the size of the groove you're creating, and the length of the blade needs to be sufficient to reach the full depth of the cut without flexing or vibrating.
So no floppy blades allowed.
Definitely not. Any flexibility in the blade can compromise the accuracy of the cut. And of course, the rake angle plays a role here as well.
Rake angle, it always comes back to the rake angle.
You're catching on. For grooving and parting, a positive rake angle is often preferred because it reduces cutting pressure.
Which is important when you're dealing with thinner sections of material, right?
Exactly. You don't want the tool to chatter or break. Now, the material of the tool itself is also crucial. High-speed steel, HSS, is a common choice. But for tougher jobs, carbide or even cermet tools might be needed.
So HSS for the everyday tasks and carbide or cermet for those heavy-duty operations.
You got it. Now, remember those diamond tools we talked about earlier? Well, they can also be used for grooving and parting, especially when you're dealing with incredibly hard materials.
Diamond tools, those are like the elite special forces of the cutting tool world. What about the techniques involved in grooving and parting? Are there any special considerations?
One of the most important things is to ensure a rigid setup. The tool needs to be securely clamped, and the workpiece must be firmly held to prevent any movement or vibration during the cut.
So it's like trying to write your name neatly. You need a steady hand and a stable surface.
Precisely. Any wobbling or chatter can ruin the cut. And, as always, choosing the right cutting speeds and feed rates is essential.
Speed and feed rates, what do those have to do with it?
The cutting speed refers to how fast the tool is moving across the workpiece, while the feed rate determines how quickly the tool is fed into the material.
So it's like finding that Goldilocks zone. Again, not too fast, not too slow, but just right.
Exactly. Going too fast or too slow can lead to problems like chip buildup, poor surface finish, or increased tool wear. And of course, let's not forget about coolant. It's essential for keeping everything cool and lubricated.
Coolant, the unsung hero of machining. It seems like every detail matters when it comes to these operations.
It does, and that attention to detail is even more critical when it comes to thread cutting, one of the most intricate and demanding machining operations.
Thread cutting. Oh, that's where you create those spiral grooves that form a thread on things like screws and bolts, right?
That's it, and it's no easy feat. Creating those precise, perfectly formed threads requires a high level of skill and the right tools for the job.
What kind of tools are used for thread cutting?
There are special threading tools that are designed specifically for this task. They come in various shapes and sizes depending on the type of thread you need to create.
So, different tools for different threads. What are some of the key things to consider when choosing a threading tool?
Well, first of all, you need to make sure the tool is compatible with the thread type and size you're working with. Threads come in all sorts of shapes and sizes, from coarse threads for heavy-duty applications to fine threads for delicate work.
So it's like choosing the right wrench for a bolt, you need the right tool for the job.
Exactly. And just like with other machining operations, the material of the threading tool is crucial. HSS is a common choice, but for more demanding applications, you might need to step up to carbide or even cermet.
And I'm guessing the rake angle is important here as well.
You bet. A positive rake angle is often preferred for thread cutting because it helps to reduce cutting pressure and produce a smooth, clean thread.
Smooth thread's essential for a good fit. What about the actual process of thread cutting? Is it as tricky as it sounds?
It can be. It involves a synchronized dance between the cutting tool and the rotating workpiece. The tool has to move in a precise helical path to create those perfect spiral
It's
grooves.
just like carving a tiny spiral staircase into the metal.
That's a great visualization. And one of the trickiest parts is getting that thread pitch just right. The pitch refers to the distance between adjacent threads, and it needs to be super accurate to ensure a proper fit.
So if the pitch is off, the threads won't mesh correctly.
Exactly. It's like trying to fit together two puzzle pieces that don't quite match it, just won't work. And of course, we can't forget about those all-important coatings.
Coatings, they're like the secret sauce of machining.
They really are. Coatings like titanium nitride, TNODN, and titanium aluminum nitride, TAAN, are commonly used on threading tools to enhance their performance and extend their lifespan.
It's incredible how much science and technology goes into these seemingly simple tools. This deep dive has already taught me so much.
Me too. It's amazing how many intricate details and complex processes are involved in creating and using machining tools.
It really highlights the ingenuity and precision that goes into manufacturing all the things we rely on every day.
Exactly. Now, are you ready to take our understanding of these coatings to the next level?
Absolutely, let's do it. Coatings, coatings, coatings. Let's talk more about those magical thin films that boost tool performance.
They are pretty remarkable, aren't they? It's amazing how such a thin layer can make such a huge difference.
We touched on a couple of types before, like titanium nitride. Can you refresh my memory on that one?
Of course. Titanium nitride, or tin as it's often called, is one of the most popular coatings out there, and for good reason. You can usually spot it by its distinctive gold color.
Ah, yes, the golden tool. So what makes tin so special?
Well, for starters, it's incredibly hard and wear-resistant, which means it can really extend the life of a cutting tool. Plus, it reduces friction, which helps keep things running cool and smooth.
So less wear and tear, less heat. Sounds like a win-win. What other types of coatings are out there?
Oh, there are quite a few, each with its own unique properties. For instance, there's titanium carbonitride, or Ti-C. It's similar to tin, but with an added boost of heat resistance.
So Taucian is like tin's super tough cousin.
You could say that. It can handle even higher temperatures without breaking down. And for those really extreme high-temperature applications, you might turn to aluminum oxide, also known as Al2O3.
Aluminum oxide, huh?
Yeah.
That sounds familiar. Isn't that what they use to make sandpaper?
It is, but in this case, it's applied as a thin coating to machining tools. It provides exceptional thermal stability and wear resistance.
It's like giving those tools a suit of armor, but made out of sandpaper.
Exactly. And of course, we can't forget about diamond, which is still the king of hardness.
Ah, yes, diamond, the ultimate in hardness and durability. Where does diamond fit into the world of tool coatings?
Diamond coatings are reserved for those really tough machining tasks, like cutting super hard materials such as ceramics or composites. They're like the heavy artillery of the coating world.
So with all these different coating options, how do you choose the right one for the job?
That's the million-dollar question. It really depends on several factors, like the material you're machining, the desired tool life, the cutting speeds and feeds involved, and the overall demands of the operation.
It sounds like there's a lot to consider.
There is, and on top of that, you also need to factor in the different methods used to apply these coatings. The two most common methods are chemical vapor deposition, or CVD, and physical vapor deposition, or PVD.
Oh yes, CVD and PVD. We talked about those earlier. Remind me about the differences between these two methods.
Sure. CVD is like baking a cake in a very high-tech oven. The tool is placed in a chamber, and the coating material is deposited onto the tool surface at high temperatures. This results in a thicker, more durable coating.
So CVD is for when you need a really tough, long-lasting coating.
Exactly. Now, PVD is a bit different. It's more like spray painting in a vacuum chamber. The coating material is vaporized and then deposited onto the tool in a very controlled manner.
I'm picturing something out of a sci-fi movie. So what are the advantages of PVD?
Well, one of the big advantages of PVD is that it can coat those really intricate geometries and sharp corners, places where CVD might have trouble reaching.
So PVD is for those delicate precision applications.
You got it. Both CVD and PVD have their pros and cons, and experienced machinists know when to choose one over the other.
It's fascinating how much thought and science goes into something as seemingly simple as a tool coating.
It really is. But that's the beauty of machining. It's a field where the tiniest details can make a world of difference.
Well, I have to say, this deep dive has been incredibly enlightening. I feel like I've gained a whole new appreciation for the intricate world of machining tools.
Me too. And I hope our listeners feel the same way.
From the materials they're made of to the coatings that enhance their performance, it's clear that a lot of thought and engineering goes into every aspect of these tools.
Absolutely. And let's not forget about the skilled machinists who use these tools to create all the amazing things we rely on every day.
To those skilled machinists out there, we salute you. And to our listeners, thank you for joining us on this deep dive into the world of machining tools. We hope you learned something new today. Until next time.